Hello everyone, I wanted to take a few minutes in this video and go over the chemistry final and give you some tips. You'll notice here that there are 30 questions and there are also 2 extra credit questions for an additional 10 points. The extra credit questions are about halfway down. The final is organized by topic. So we start with the topic of gases and gas laws, which we spent quite a bit of time on. Question 1 is just a simple matching question. So you'll need to write the correct letters over here next to the terms on the left. There are 5 gas laws. Question 2 deals with the term standard temperature and pressure, STP, which was a term that we used a lot in the gas laws chapter. Not to be confused with standard conditions or standard state conditions. That's a different term that we used when we got to thermodynamics. So if you don't remember the exact temperature and pressure, you'll need to look that up. Question 3 deals with the combined gas law, and all of the information you need is given. Now I will give you a little reminder. When you use the gas laws, you need to convert temperature to Kelvin, because we have to use absolute temperature in order for the gas laws, including the combined gas law, in order for them to work. The rest of the information is pretty straightforward. You're given volume in liters, you're given pressure in atmospheres. So this is basically a plug-and-play type of problem. You're given a hint here. Question 4 is asking about the ideal gas law. You'll notice that in both parts, the conditions are listed as STP, standard temperature and pressure. So you'll need to use those here and here. N, as you recall, is the number of moles, and that's what both of these are asking. Now you'll need to be careful in using the correct value for R, the gas constant. You'll need to use units for R that match the other units, because R can be expressed in different units. And so your textbook will give a table, or you can look up a table on the internet that lists the value of the gas constant R using different units. You want all the units in this formula to mesh so that they will cancel out. And you're given hints in both questions. The next subject is solids and liquids. And in question 5, it's asking for the 3 groups of that's important, intermolecular forces. And these are given in your book. We went over them quite a bit in class and in homework problems. Number 6 is explain from a chemistry standpoint why ice floats on liquid water. So don't just say ice is lighter or less dense than liquid water. That's not good enough. So you need to explain, from a chemistry standpoint, what happens in the case of solid water or ice. Question 7, give definitions of evaporation and boiling. We spent a lot of time on this in class. There are definite differences. Do not just say evaporation happens at room temperature and boiling happens at boiling temperature. That's not good enough, because I can get water to boil at a very low temperature, and evaporation happens at hot temperatures too. So there are definite differences, and we went over these at length in class and in different problems. Question 8 is dealing with vapor pressure, which is a topic covered in your books in this chapter. And it's really a graph reading problem. Can you read a graph? So this is the kind of problem you would see on pretty much any standardized chemistry test. And so you'll need to be able to read the graph. You'll need to look at the compound. In the first one it's ethyl alcohol. And you'll need to look on the green curve and be able to read the graph. And so it's really a graph reading type of problem. Next topic is solutions. We spent a whole session on this. It's asking about molarity. So whenever you encounter a question like that, just remind yourself of the definition of molarity. It's moles of solute divided by liters of solution. So the first one, A, is very easy because you're given the number of moles of solute and you're given the number of liters of solution. So it really couldn't be any easier. The second one is a little trickier because you're given the amount of salt or solute in grams. And so you'll need to figure out the molecular weight of potassium nitrate. I did an example here. If the solute or salt was calcium chloride, you figure out the molecular weight like this. And we've done this so many times in class now and in homework that you should know how to do that. That's how you would figure out the molecular weight of calcium chloride. So you will need to do that with potassium nitrate. Figure out how many moles are in 100 grams and plug that into the molarity formula. Problems 10 through 15 are set up as kind of a practical environmental problem. It says you have been retained, that's a word that means hired, by a company to give your advice and recommendations on treating their wastewater. So this is a very practical type of problem. We've done, I think, at least 2 labs that dealt with this problem, and we've had homework assignments just like this in the past. Question 10 says you begin by doing some testing, always a good place to start, and determine that their raw wastewater has a pH of 6 and the level of dissolved copper in the untreated waste stream is 100 milligrams per liter. A, is the raw untreated wastewater acidic, neutral, or basic? So you'll need to determine if a pH of 6 is acidic, neutral, or basic. B, if you treat an average of 1 million liters of wastewater per day, which is not uncommon, how much copper in grams is present in this amount of raw wastewater? This is a very easy, straightforward question. You have 100 milligrams per liter, and you have 1 million liters. And so it's a very simple problem. You'll need to convert your answer to grams, as you can see here. Question 11, we are referring to a chart we've looked at in class, and it's asking what pH would result in the copper being the least soluble. That's what you will need to do for your client. You'll need to drop the copper out of solution. We did at least 1, maybe 2 labs in which you did exactly this. So this is a chart reading question. You'll need to be able to look at the X and Y axes on the chart and find the curve for copper and find the pH that it's asking for. Question 12 sort of lays out your recommendation to the client. If they raise the pH to the optimum level, which you just determined in the preceding question, if you raise the pH and then allow time, a couple hours or whatever, for the resulting sludge to settle, you estimate that the level of copper remaining in the top half of the water of the waste stream could realistically be reduced to this level, very low. So in our lab, we dropped out the copper as a sludge in the bottom of the graduated cylinder, and after time, after about 2 hours, the water on top, which is called supernatant, is very clear because it doesn't have very much copper in the top. So you can scoop the sludge off the bottom or empty it out through a valve, and the water on top is treated. And this is what we messed around with in our lab. Well, question A, given that you need to treat that many liters, the same number of liters in the preceding question, how much copper in grams would that represent in 1 day's worth of treated wastewater? A very easy question. So you're given the level of dissolved copper in milligrams per liter, and you're given the quantity. How much copper does that represent in grams? You'll need to convert your answer to grams. Part B then says that the facility is permitted by the Environmental Protection Agency. That's a branch of the government that regulates pollution. And you can discharge, or your client can discharge, no more than 25 grams per day down the sewer. Well, based on your calculations, would the facility be in compliance? In Part A, you just calculated how many grams they would be discharging down the drain from this clear supernatant. Is that in compliance or not? It's a pretty easy question. Question 13, it was stated that you would somehow need to raise the pH of the incoming wastewater to drop out the sludge. We did this in our lab. We actually played around with several different bases to see which one, worked the best. And so this is giving you some possibilities, and it's saying which one would not work. To raise the pH from 6 to the optimum level that you calculated above, I think it was in question 11. So a pretty straightforward question. Now you have 2 extra credit questions, and this is a cutaway drawing of what's called a clarifier. They can be very large. They could be 10 feet across, going this way. They could be 100 feet across. Just depends on what you're trying to do. But this is very common, typical equipment that's used in industrial wastewater treatment. And so it's asking you to kind of size the equipment for your client. If they directed their untreated wastewater to a central treatment plant, which would include this equipment, and you figure it takes 2 hours, that's an important number, to settle the sludge, which technically is called flock, to the bottom of the clarifier tank. We did all this in our lab. In other words, you need 2 hours retention time in the clarifier. And, assuming the treatment plant can run 24 hours a day round the clock, how large must you design the clarifier tank in liters? Okay, so you'll need to remember, in a previous question, you were given the volume of wastewater per day that you were supposed to treat, and so you'll need that in order to solve 14. 15 is a geometry problem. If the clarifier is circular, like it is shown here, it's just a cylinder, and you needed a liquid depth of so many meters, what would the inside diameter of the tank need to be in order to handle the volume that you calculated in question 14? So this really comes down to geometry. It's a geometry question. Okay, the next topic is thermodynamics. Thermo, we spent quite a bit of time on this. Standard conditions. What is meant by standard state conditions? In other words, state the exact temperature and pressure that correspond to that term. Question 17, heat of fusion. It's asking, first of all, what is the heat of fusion of water in kilojoules per mole? You'll just need to look it up. It's probably in your book in a table. If you can't find it in your book, you can find it online. But you need to get that number in kilojoules per mole. B, how many moles of water are in 1,000 grams of water? So this will require you to calculate the molecular weight of water, a pretty simple problem. You've done it 100 times in homework problems prior to this. And then once you know how many moles it is, and you know the heat of fusion in kilojoules per mole, part C gets pretty easy. It says how much energy in kilojoules would it take to melt 1,000 grams of water from ice to liquid water at 0. So we're talking about the heat of fusion. We're not heating it up past 0. We're just starting at 0, we're melting it, and ending at 0. That's what's called the heat of fusion. Question 18 is sort of the next step, and it's dealing with the specific heat, which was the letter C and the little subscript SP. And it says, what is the specific heat of water? This time in joules per gram degrees C. So your book contains tables. If you want, you could look it up on the internet. It says now convert that number into kilojoules per gram degrees C. You need to know how to do conversions. How much energy in kilojoules would it take to raise the temperature of the same 1,000 grams of water now that you've melted it in question 17? Now you're going to heat it from 0 to 100 degrees C as a liquid. You're not going to make it into steam. You're going to stop at 100 degrees C as a liquid. And so we're dealing with specific heat. Okay, question 19 is the third and final step. It involves the heat of vaporization. So now you've got your 1,000 grams of water. You've heated it up to 100 degrees Celsius. Now you're going to boil it. So you'll need the heat of vaporization, sometimes called the enthalpy of vaporization, in kilojoules per mole. You'll need to look it up. Once you get that, it's asking how much energy would it take to boil the 1,000 grams of water at 100. So you're beginning with liquid at 100 and you're ending with steam at 100. You're not going past 100. Question 20 is putting it all together. And you've done this, I think there's been 2 or 3 homework questions where you did almost this exact problem prior to this. It's asking you to add the 3 steps. Go from ice at 0 all the way to steam at 100. And then it's asking you to just analyze it. What step requires the most energy input? Step 1, step 2, or step 3? Next topic, chemical kinetics. We spent quite a bit of time on this. Kinetics, again, is dealing with the speed of chemical reactions. So the rate is some constant that has to be experimentally determined. Don't worry about what it is. Times the initial concentration of A squared times the initial concentration of B to the first power. And the concentration of C doesn't matter for whatever reason. It's C to the 0th power. And it's asking which of the following changes would have the least effect. So you kind of have to look at each one and make a little mental note. Does that increase the rate or not? And kind of keep track as you go down. And you have to look at all 5, and then you have to pick the best one after you do all that, because it's kind of worded in reverse. Working in your spare time in your home laboratory, which is depicted here, you discover a new method of producing a substance called C. Of course, you're going to name it after yourself, but for now we're just calling it C, which is a polymer, kind of a plastic, having the strength and weight characteristics of titanium. Wow, that's a very strong and lightweight metal. What makes this discovery especially interesting is that it has a market value very high, $50 a pound, and you can buy A and B for only a few pennies a pound. So there's a definite profit opportunity here. So the reaction can be written as shown here. 2 moles of A plus 1 mole of B yields 2 moles of C. All right, so I want to go over this very carefully because this always confuses people, the way it's written, so I want to make sure you understand what's going on. You then set out obtaining the following data concerning the rate of the reaction. In other words, you've just invented a reaction. You've figured out what the formula is. You've been able to measure the ratios of the reactants and the products, and you've at least figured out the stoichiometric formula for the reaction. But you don't have any solid numbers as to how fast the reaction occurs and how it responds to changes in A and changes in B, for example. And this is useful information you need. So you set up 3 experiments. That's what's meant by run 1, run 2, and run 3. You set up 3 experiments in your home lab where you vary the initial concentration in a very careful way. And you measure the rate of the reaction that results. The higher the number, the faster the reaction. You want to have a fast reaction. Presumably, you want to commercialize this process so you can make money and patent it and sell it and do all that. So you want a reaction that's, relatively quick. You don't want to sit around for months for the reaction to happen. So you start with an initial concentration of A and B in trial 1 or run 1. And this is in moles per liter. These are just numbers that you've been able to measure. And you get a rate. You're able to measure the rate that the reaction occurs in moles per liter per second. Okay, on run 2 or trial 2, you vary the initial concentration of A. As you can see here, you doubled it. You doubled it because it makes the math easy that way. And you measure the initial rate of that reaction. And voila, you notice that it has increased. In fact, if you look at the 2 numbers, you can see it's increased 4 times. It's 4 times faster, and all you did was double A. All right, you want to see how it responds to B. So you crank A back to where it was, and this time you double B. You look at the initial rate of that reaction, and you notice that something happened, and you can compare it with the original. See, it's different. Something's different about it. Now you continue on. The general rate of the reaction is here. This is just the generic, prototypical, kinetics reaction rate formula. At this point, you don't know the values of the constant, and you don't know the values of the exponents x and y. They could be 1, 2, they could be 0, they could be 45. You don't know what they are. And that's why you're running these 3 trials. And that's going to ask a series of questions. So using the results of your 3 runs, what is the reaction order for each of the reactants? In other words, what is the value of x and y up here in this formula? That's what we mean by reaction order. You monkeyed around with the initial concentration over here, and you observed how the rate of the reaction responded. And that tells you, those are clues that tell you what the x and the y are. And so you will need to look at the rate equation. And this is exactly the kind of problem you'll see on standard tests, the SAT subject test in chemistry, for example. What is the value of k? So the next thing you have to do, once you figure out what x and y are, then you can kind of rewrite the rate equation a little more specific. So maybe it's k times a to the something power, b to the something else power, but you still don't know what k is. There was at least one homework problem, I think multiple homework problems that went over this. It's also given in your textbooks. So what you'll want to do is go back and take one of these trial runs and plug it into the formula, and that will give you k. And then finally in part 3, write out the entire rate law. So you're not just writing out rate equals k, ax, b, y. You're actually writing in a number for k, and a number for x, and a number for y. Chemical equilibrium was the next big major topic we covered, and chemical equilibrium answers the question, how far does a reaction proceed before it stops going? It reaches equilibrium, in other words. Some reactions go all the way. Basically, if you light a bunch of gunpowder on fire, it's going to oxidize all the way. But most reactions do not. They reach some kind of equilibrium. So we're given a hypothetical reaction, and you're asked to write out the equilibrium constant expression. So just as a hint, it's products over reactants. And you write C with square brackets, which means the molar concentration of C, to the cth power. Do not write C times C. That doesn't even have any meaning in chemistry. We're using square brackets to indicate molar concentration in moles per liter at the point of equilibrium. And you're using the prefix as the exponent, and you're writing products over reactants for the equilibrium constant. So if you don't remember that, go back and review it in the chapter. Le Chatelier's principle was a very, very important principle we studied ad nauseum in that chapter. If you don't remember what that dealt with, do go back, take a few minutes and go back and review it. This question involves gases. Everything is in the gas phase, so it makes it easier. And you're given 4 choices. And so you'll need to kind of think about in terms of gases, how many moles of gas are involved as reactants and products in each one of these. And I think we had a homework problem exactly like this. Question 25, the formation of glucose. Okay, this is maybe the most common chemical reaction on planet Earth, because if you look out your window, just about everything you see is made out of long chains of glucose molecules, which are joined together to form the plant kingdom. Everything in the plant kingdom is made out of starch, cellulose, lignin, and those are just long chains of glucose molecules. So this is the process of photosynthesis, taking water into the plant, usually through the roots. Some plants can get water through the leaves. You're taking in CO2 into the plant through the leaves, right out of the atmosphere. It's grabbing CO2 out of the atmosphere, and it's building the molecules that are needed to build the plant. So this is basic biology here. And we're given equilibrium concentrations in moles per liter. So it really couldn't be any easier here. It says calculate the value of the equilibrium constant. Now, the only trick with this question is you'll notice that glucose is given as a solid, and without giving away too much information, we do something with solids and also with pure liquids when we write the equilibrium constant. We treat them in a certain way. If you don't remember what that is, go back and read it in your book. All the others are written as a gas, which makes it easy. So it's a plug-and-play type of problem. K equilibrium, again, is products over reactants. You can see what the prefix or the coefficient each of these is, and so all the information here is given, and it's a plug-and-play type of problem, and you'll need to be very careful keying it into your calculator. Okay, 26 is another Le Chatelier's principle problem. You'll need to review this in your book. After patiently experimenting in your home lab for 6 months, you have discovered that you can economically, see, the important word here is patiently. You can economically produce substance C, a much sought-after compound used in the pharmaceutical industry, and you can charge a lot for it. So here is the reaction. It says, as part of the commercialization of the process, you are trying to figure out how to shift the equilibrium further to the right. That's the essence of Le Chatelier's principle. Anytime you're trying to develop a commercial process, you want the reaction to go to the right. So you use Le Chatelier's principle to do that. And so you'll need to take some time and probably review that in your textbook. Okay, next topic, acids and bases. You only have one question on acids and bases. It concerns the formula for pH. And you're given two different acids, hydrochloric acid and sulfuric acid. The only trick with sulfuric acid to remember is that it's diprotic. There's two hydrogens. So whereas when hydrogen chloride or hydrochloric acid, you mix it with water, and it dissociates into the hydrogen ion, but the hydrogen ion doesn't stick around by itself. It combines with the water molecule to form the hydronium ion, and the negative anion, the negative ion or anion, is chloride. That's how hydrochloric acid dissociates in water. So if you have this concentration of HCl, you're going to have the same concentration of hydronium ion. Once it dissociates, it only takes a second. It's a very strong acid. The trick here is that with sulfuric, you have two hydrogens. So when it gets dissolved in water and it breaks down or dissociates, it forms two of these guys and one of these. Now that's not balanced. I need to put a 2 here in front of the water in order to balance it. But you'll see that for every one of these that you're playing around with, you're going to get 2 of these. That's the difference. So keep that in mind when you're plugging in the value of the hydronium ion concentration. Otherwise, this problem is very, very straightforward. So you'll need to locate the log button on your calculator. Next topic is organic chemistry, so you need to review this in your books. First, hydrocarbons. Where do we get hydrocarbons? They come from oil and gas. What two elements do they contain? You'll need to look that up. What do the terms saturated and unsaturated mean in terms of chemistry when applied to hydrocarbons? Be specific in terms of chemistry. Classify these. Okay, you'll probably need to look those up in your books. Give the general formula for alkanes, alkenes, and alkynes, or as they say in Great Britain, alkins. And lastly, draw or type in the functional groups, sometimes called general formula. I think most of your books are going to call them the functional groups for these. And these are the 6. Okay, if you have any questions about the way any of these problems are worded, just let me know.